Welcome everyone. We are starting today a new topic. It's about genetic and evolutionary algorithms. And I'm going to start with some examples of problems which are too difficult to solve with conventional methods, and then explain the notion of evolution and how these human evolution concepts from human evolution have been converted into computational models. And I will introduce one of these models. It's called a genetic algorithm. I will explain the basic principles and operators of this method, and also a few things about its convergence. Then another algorithm of this type, it's called the evolutionary algorithm. I will explain the stages, the differences from the genetic algorithm, and give you some examples of pseudocode that work along these lines. I will finish with some examples that illustrate the use of the different operators. First, I'm going to start with an example of a problem which has been solved with genetic algorithms. It's Bloomberg's European headquarters building in London in 2018. And this is the atrium, one of the most fascinating parts of the building. And you see the design. This is an example, this is a project where genetic algorithms have been used. And this is the statement by Foster and Partners, the company, the architects of this project. They used, as I say, optimization algorithms usually used in the field of artificial intelligence. These are genetic algorithms, basically, which can be used to try different alternative designs, find the optimal one, and then also solve the design problem that was a difficult building to manufacture because you had to calculate the steel details for the atrium for the whole building and for the whole building. Here are some other examples of problems. For example, we have a situation where the search space or the complexity of the objective function does not allow the use of conventional methods. And I have a simple example here. It's a function that depends on 100 variables. Each variable can either be 0 or 1. The search space is 10 to the power of 30. It's impossible to perform an exhaustive search and find the optimal combination of parameters. Another type of problem is the TSP, the travel salesman problem. It's a short path optimization problem. And in this case, for example, we have 10 cities and you can see 181,000 possible combinations. If you go to 50 cities, then we are talking about 10 to the power of 22 possible solutions. Clearly solving this kind of problem with traditional optimization, it's not very simple. GAs, evolutionary algorithms, swarm intelligence, which I'm going to present in another lecture, has performed very well in TSP problems. Another kind of problem is the so-called global optimization problem. And I have an example here from a function which is typically used to illustrate and global optimization problems, and also used as a classic benchmark in global optimization algorithms. This is the so-called Levy number 5 function. It has 760 local minima and only one global. It's an artificial problem, so we know exactly where the coordinates of the global are, and you can see on the slide the analytic form of the fitness function. This diagram shows you the function in the interval -10 + 10. Other kind of problems in real life, there are many problems that have been solved with genetic algorithms and evolutionary algorithms. These are typically examples where we have to optimize a function and the variables are the solutions need to be within certain bounds, or there are constraints that we have to satisfy. And there are many problems of this type, like timetable problems, design optimization problems. And I have some examples quickly to give you to illustrate how this thing works. For example, in the domain of architectures, you can see here some of the projects that have been solved with genetic algorithms with the use of a particular package. It's called Grasshopper, and basically uses GAs to find optimal designs. And on this page, you can see some of the applications. You can go to these links by clicking the corresponding links in the slides that I have posted on Moodle. Another kind of problem, again, in design problem is this one. When you have where GAs are used for energy efficiency, and the algorithm runs, and you can see how the designs change, and as the design change, different parameters are investigated and their fitness is judged in order to find the optimal combination that will satisfy some constraints. In the field of artificial intelligence and neural networks, this is a classic example where neural networks evolve through the use of evolutionary algorithms. And I'm going to have another lecture where I'm going to focus more on the use of GAs in neuroevolution, the so-called neuroevolution.
Here.
So you
You're
see, for
watching a
example,
skilled
this
player play Super
video,
Mario
it
World.
illustrates
But this player is not
how
human.
neural networks,
It's a
it's not
computer program I wrote
human
called
player,
Mario.
it's a neural network
This program
that
started
is
out knowing
trained
absolutely nothing about Super
on
Mario
different
World or Super
games
Nintendos.
and gradually
In fact, it didn't even
learns
know that pressing right on
to
the
play
controller would make the player
the
go towards
game
the end of the
and
level.
also finds
It
very
learned
good
all of these
strategies
things
actually
through a
to win
process called
this kind of
neuroevolution.
game.
In this video, I want to teach you about
another area where designs, GAs have been used. It's this one from NASA for the problem of evolutionary antenna synthesis, how we can find, optimize the design of the antenna, optimize energy consumption, and maximize power, so that is used a lot in, it's a classic way to design in different kind of space missions. And there is a Wikipedia, have the link on the slides again about evolved antenna synthesis, so you can see how this thing works to optimize the design of antennas using satellites and also in spacecrafts. So let's go back now to the lecture. As I said, the whole idea behind GAs is the theory of evolution, biological evolution, and we can also combine learning with evolution and create more adaptive forms when it comes to artificial intelligence. I'm going to have another lecture on this topic because it's one of the most advanced ways to produce AI combination of creating hybrids between evolution and learning. So evolution is a process which involves selection, reproduction, and gradually a population of individuals adapts to different to the environment and survives. And learning, on the other hand, it's more about adjustments that take place within the lifetime of an individual. Like, for example, when we adapt the parameters of a neural network, the weights of the neural network. So as I said, I will have more about evolution and learning next week when I'm going to start my sessions on the advanced learning schemes and the hybrid systems. I'm going to cover this topic for a couple of weeks. So how we simulate evolution in a computer? We produce a set of optimization algorithms which are run, and we can simulate how the members of the populations evolve from generation of generation, and they find the optimal solution. The approach is based on natural selection and genetics, and it covers different methods like evolutionary algorithms, genetic algorithms, evolution strategies, genetic programming. In this module, I'm going to talk a bit about genetic algorithms and evolution strategies. I'm not going to cover genetic programming at all, unfortunately. I don't have the time to do that. So in evolutionary computation, members of a population adapted from generation to generation, and the best individuals survive, and they become able to predict changes in the environment, and they become more and more fit. That's the basic idea. I like to have a couple of slides on the history behind the use of the algorithms. So, for example, it's worth mentioning Charles Darwin. He presented the theory of evolution in 1858. The theory of evolution of Darwin's theory of evolution, together with the theory of natural selection and concepts of genetics by Mendel, now represent the so-called new neo-Darwinian paradigm. And you can have a look on Wikipedia. There's a nice article about the 20th century view on evolution theory and the combination of the different paradigms. The whole process of evolution, it starts with the population and aims at making individuals, the members of the population, survive and reproduce so that they can perform well in a specific environment. The whole ability of the members of the population to perform well is judged by the so-called fitness function or evolutionary fitness. So it's a measure, this is a measure of the organism's ability to predict changes in the environment and adapt. And in GA's algorithm, this kind of evolutionary fitness is represented by a form of cost function or objective function or a kind of equation, basically, that we use to calculate the performance of the different members of the individual and make decisions. I have a simple example here from nature. So it's a population of rabbits. Some rabbits are faster than others. So we can say that they possess superior fitness compared to others because they have greater chance, and because they are faster, they have greater chance of avoiding foxes, surviving, and then breeding. So if two parents have superior fitness, then there is a good chance that their offspring will also have a good fitness, even higher fitness than their parents. So over time, the entire population of rabbits will become faster and will be able to predict environmental changes and survive foxes. That's the whole idea, and these kind of concepts have been translated to operators and used to compute, to model evolutionary algorithms. So all type of evolutionary computation algorithms, somehow they simulate natural evolution by creating a population of individuals, evaluating the fitness or performance of the individuals in a particular context, generate new populations through the use of some genetic operators, which I'm going to explain, and then this process is repeated for a number of times or until we reach the maximum number of generations, or until we reach some kind of criterion that relates to the values of the fitness function. So I'm going to start with genetic algorithms and gradually introduce this kind of concepts. GAs were proposed in 1970s by John Holland. He basically had a project working on string manipulation. So he was trying to find effective ways to parallelize algorithms to manipulate strings of binary digits. And he came up with this idea. He introduced the concept of the artificial chromosome. The chromosome usually consists of genes. So we follow the same kind of concept here. We have the artificial chromosome, and the artificial chromosome consists of some elements. These are genes, and each gene is represented by either 0 or 1. So as you can see on the slide, we are basically building a kind of binary string, which represents a chromosome, and the chromosome is a representation of an individual member of a population. And he also introduced concepts which are very important for the operation of genetic algorithms. They currently used in every algorithmic model that follows these principles. So we have to decide what kind of encoding we are going to use and how we are going to evaluate the fitness of the members of the population. Based on the evaluation of this fitness, the GA the members of the population are going to be reproduced. Reproduction takes place using operators like crossover, where members of the population exchange parts of their chromosomes, and the mutation, where the operators, it's a kind of operator where changes the values of the particular gene, usually chosen randomly from the chromosome. These are important operators which affect the performance of the members of the population. Crossover is used obviously in human biology. Mutation, exists in human biology, but it's usually associated with malformations, so it's not really a desired operation. And you can see the basic principles and the basic steps of genetic algorithms on this slide. So we randomly generate an initial population of chromosomes. We compute the fitness of every member of the population. We apply selection in order to produce an intermediate population. The selection selects the most promising individuals from the population. We generate a new population by applying genetic operators, crossover mutation. The operators are applied on the members of the intermediate population that we have produced. And if the members of the current population satisfy the problem requirements, then we stop. Otherwise, we go back to step 2. So we evaluate again the fitness of the members of the population. We select most promising members for reproduction using crossover and mutation, and we iteratively follow this kind of model. So if I have a fitness function, and I have a simple example here on a 3D space, that's an example of function, for example, then what happens in the first generation is that we generate some members of the population, usually randomly. These are the black dots that you can see on the slide. And through the process of crossover reproduction, crossover and mutation, and evaluation of the fitness of the individuals, gradually the GA is going to move the different members of the population towards a global minimum. And the global minimum you can see here in generation 10, the points start moving towards the global, which is on the center of the figure around the point 0,0. As I said, the fitness is an important parameter. It depends on the problem. The right choice of fitness, it's an important choice, and it's left to the designer. The designer will have, of the GA algorithm, will have to make a decision about the right form of the fitness function. And I have an example here for the fitness function that we used in past research for to model a steel works plant. So in this particular case, the fitness function is the total monthly cost, which is given by the investment cost and the waste monthly cost. And the investment cost depends on the size of the factory. And you have normally some kind of parameters like the number of torpedoes, the number of cranes, the number of steel furnaces, the volume that each torpedo can hold. And these are all parameters of the fitness function. And the aim is to basically minimize the waste and minimize the total monthly cost, which is really is affected by the amount of waste that the plant produces. And in the slide, you can click the link and see more details about the problem in an appendix. As I said from the beginning, an important design decision is the encoder that we are going to use. We use normally in a problem that we want to solve with GAs, we have a number of variables, and the variables normally can take binary values or real values. Okay, so it's an important decision whether we're going to work with binary or with real values. The standard form of a genetic algorithm usually has binary values. So even if our real problem requires real values, we would have to find a way to transform real values and code the real values into binary strings. Okay. If the problem is binary, then usually situation is simple because you can have a representation with binary strings where the genes in the chromosome can be either 0 or 1. So it's somehow simple to solve. It really depends on how many bits you are going to have, because the number of bits, obviously, it's like in computing. The higher the resolution you have, the more precision you can have. The shorter the number of bits for each to represent each one of the values, the more rough, in a sense, the solution, the search will become, and the GA will work. If you have a real value problem, so your variables x1, x2, x3 can take any value in the interval, let's say 0, 1, then you have to have a form to transform the real values into binary. And this is what I have done here in a simple way to show you how things work. For example, in this case, I have 8 bits precision only, which means that the 0 is 0, 0. It's a binary string 0, 0, 8 zeros, and 1 is going to be a binary string where all bits are going to be 1. And then since I have 8-bit precision, the smallest number that I can represent is the real number 0.0039. Okay, so that's the smallest real value I can represent. If your solution requires smaller values than this one, this GA with 8 bits representation is not going to be able to find it. Okay, that's why it's an important decision. Okay. Naturally, one could say that, look, okay, I increase the number of bits, so I don't need 8-bit precision. I need, I don't know, 16-bit or 32-bit precision. If you have the computational resources to solve the problem with, I don't know, 64 bits, then of course you can go ahead and you can do it. If you don't have the resources, then you have to use a shorter encoding, which might affect the quality of the results. So, for example, if my vector has 3 variables, x1, x2, x3, like in this case, then I can represent it as a binary vector, where you can see that the first 8 bits correspond to a value of for x1, the second set of 8 bits, a value for variable x2, and that third set of 8 bits represent a value for the variable x3. If I can use real values, then I can directly encode my the members of the population in using real values. Normally, if I can do that, then I would have to create bounds for then allowed values, because otherwise it's extremely difficult to do calculations. As I'm going to explain, the GAs use randomness, so you may come up with solutions which are not suitable for the problem. The GA, if you don't use bound, may produce solutions which you cannot really implement in your design. Clearly, if you use real values, there are advantages because you can have increased precision, you can have shorter strings, and you can also use special genetic operators. You can even define your own operators. So it gives you a lot of flexibility. Okay. An important parameter operator actually in genetic algorithms is the selection operation. Okay. The selection creates a subpopulation which is used for reproduction. There are different kinds of selection operations. I will explain some of these mechanisms here. The idea is that you have a group of chromosomes. These are called parents, parents, and these are selected through some kind of method or function, which is called selection function. So the genes of the parents are mixed and combined to produce offspring for the next generation. Okay, the role is very important, as I'm going to explain. The idea is that by going through this process, the bed chromosomes will survive and will be selected for reproduction, and then the offspring will be better than their parents, and they will have higher chance of surviving in the next generation. And this whole process emulates the so-called survival of the fittest mechanism that was introduced as part of the Darwinian theory of evolution. So I have some examples here of selection schemes. There is the so-called proportionate reproduction. Individuals are selected based on their fitness relative to the fitness of the rest of the population. There is another mechanism, it's called tournament selection. The members of the individuals defined are selected at random, but it depends really on kind of tournament between that takes place, and the tournament size is one of the parameters that the user has to define. I have some high-level description of the schemes here in this slide. That's the roulette wheel selection, one of the most commonly used techniques of the proportionate selection mechanism. So we calculate the fitness of all members of the population. This is n capital. We generate a random number n between 0 and the total fitness n capital, and return the first population member whose fitness added to the fitness of the preceding population members is greater than or equal to n. That's another scheme. It's called deterministic tournament selection. The best fit individual of the tournament is chosen for reproduction. The simplest version is the binary tournament. So we have a tournament size of 2, and we compare 2 individuals. The best one is selected for reproduction. So this kind of function takes as an argument the population and the tournament size, and makes comparisons, selects randomly a member of the population, compares with the best fit individual so far, and makes a kind of comparison. And you can do like, because this is based on random sampling, you can have, you can do resampling, or without resampling, depends what kind of version you're going to use. And in the literature, if you Google, you will find there are different approaches people have tried to improve selection, the selection mechanism. So the winner of each tournament has the best fitness. It's selected for crossover. In mutation, mutation alters the gene in the chromosome, and you can have the operation depends on what kind of encoding we are going to use. So if you use binary encoding, it means that our chromosomes have only binary digits, 0 and 1. So we alter randomly 1 bit. The alteration happens with some kind of probability. In this context, this is called mutation rate. And we use small values for the mutation rate because, as I said, mutation in typical GA is not an operation where we want to happen frequently. Okay. If you use real encoding, then the whole operation mutation is similar to a kind of noise operation. So there are, for example, models which follow the Gaussian mutation. Basically, what happens is that since you have real value encoding, X, a member of the population, is a real number. And what we are basically doing is that we take the original number and we add some kind of noise using Gaussian number generator. So the noise follows the model, the average, the mean is 0, and the standard deviation is sigma, the standard Gaussian noise. But in our case, the standard deviation is called the mutation step size. Okay, and there are different ways to select this mutation step size. I have a diagram here to show you how things work for a binary encoding. So basically, you have a binary string, like in this case, 101101, and we select one of the bits. This one, you see the red cross here, and this is going to be altered. It will become, it was 1, it becomes 0. The idea of mutation is to introduce diversity in the population and avoid the problem of premature convergence. Okay, we have found that introducing diversity helps the GA converge to a better solution. So as I said, this happens with a very small probability because usually it's not desirable. The use of a lot of mutation does not have a desirable effect. If someone uses just mutation without crossover, then the whole process simulates a random walk through the search space. It becomes like a random search. So mutation, as I said, we randomly mutate bits. We select randomly the positions of the bits where are going to be mutated, and we just flip the bit from 1 to 0, from 0 to 1, like in this case. There's another technique which is called in-order mutation. So 2-bit positions are randomly selected, and only bits between these 2 positions are mutated, like in this example, where the black becomes white and the white becomes black. Some more examples here. Binary encoding and bit mutation is used on the 4th bit. So you can see the original chromosome and the new chromosome. Since the mutation was applied to the 4th bit, that changes from 1 to 0. Some examples and more details about mutation in the context of real value encoding. I already referred to Gaussian mutation. This is basically the use of Gaussian random noise, mean zero, and standard deviation sigma. Sigma is called mutation step size in our case. I explained about that already, but it is possible in GAs to use adaptive mutation step size, and you can see here different ways someone could adapt the mutation step size. So you can say you can change the mutation step size according to this kind of formula, which takes into account T is the number of generations, T capital is the maximum number of generations. Usually in GAs, you have to set the maximum number of generations. Otherwise, the process may evolve in time indefinitely. There are ways, algorithms that have used a personal step size to each member of the population. So the individuals, each chromosome can have its own step size, as you can see on the slide. It is also possible to assign a personal step size to each variable of each individual. You remember, the chromosome represents different kind of variables. These are represented with binary strings or with real values. So each one of these variables in the chromosome can have its own individual step size, mutation step size. So you apply mutation in different ways and you adapt the mutation step size for each one of the variables. It gives a lot of flexibility in the design, as you understand. Some more examples here. I have two parents, and you can see in the first column, and I apply 1-point crossover with crossover site 3. So after the third bit, we apply crossover, and you can see the offspring that are which are produced. Basically, the first 3 bits come from the first parent for the first offspring, and the rest of the bits come from the second parent. Okay. So that's the general idea. This is called 1-point crossover. And we apply 1-point crossover according to some kind of probability. The probability is called crossover rate, because crossover is something that happens a lot in nature, in human biology. We want it to happen frequently, so we use values which are big, 0.6 to 1. We apply it with high probability because it's the operators that GAs use more frequently. You can have other concepts, other ways to apply crossover, like the multi-point crossover. So you have 3 sites where you can apply crossover. And as you can see here, we apply crossover at these 3 points. So what happens is that you produce offspring where the first part comes from the first parent, another group comes from the second parent, and so on. And you mix genes of the parents to produce the offspring. Okay. Another approach, which is very, very useful in practice, the so-called uniform crossover. So we define a mask. This is called crossover mask, and you can see the crossover mask here, 0, 0, 0, 1, 1, 1, 1. And what happens is that by applying this kind of mask, we are going, if it's 0, we are going to pick the first 3 genes from the first parent. When it is 1, we pick the 3 genes from the second parent. 0 again, we pick the gene from the first parent, and we continue like that. And in this way, we produce the 2 offspring. Okay. Some more examples: 1-point crossover with crossover site 3, and you can see how they mix. The first 3 bits, let's take the first offspring. The first 3 bits come from the first parent, and the rest of the bits come from the second parent. And 2-point crossover with crossover site 4 and 7, cut after the 4th and 7th bit, and then the first 4 bits come from the first parent, then 3 bits from the second parent, and the last 2 bits again from the first parent. And 2-point crossover with crossover site 4 and 7 is going to give you the same kind of offspring. But as you see, the process slightly changes, because you're supposed to take, for the first offspring, first 4 bits from the second parent. Then you keep the part in the middle unchanged, and you complete the chromosome with bits from the second parent. Some typical values, there is a lot, there are heuristics, as you understand, these kind of methods, crossover rate, mutation rate. These are basically heuristics that we need to decide what kind of values they are going to take. And there are some guidelines for large population sizes, more than 100 members in the population, crossover rate 0.6, mutation rate 0.001. These are some starting points. For small population sizes, let's say around 30, crossover rate 0.9, mutation 0.01. Okay. Smaller number of members in the population, you increase, as you can see, the mutation. Why? Because you need diversity. Diversity allows you to search better the search space. You don't have many members in your population, so you need to introduce a lot of noise, in a sense, to allow you to change the positions of the individuals of the population and better cover the search space. Apparently, if you have a large number of population, then you can quickly find suitable solutions. So it basically depends on what kind of computational power you have. If you have computational resources, then you can use a large population, 1,000 individuals, for example, and quickly search the space if you have the right number of computational resources. An interesting operator, it's called elitism. It's an optional characteristic of GAs. It makes sure that the fittest chromosome of the population is passed, remains in the population, and can never be replaced by other chromosomes. This is necessary because, as we said, selection is very important. Selection, each time at each generation, selects what kind of individuals are going to be used as parents in order to produce offspring. And what normally happens is that the offspring are better than the parents, and so the parents die. So if you think that there is a kind of solution, the solution is represented by a chromosome, which has some important characteristics, and this should remain in the population, okay, then you have to use elitism. Make sure that this particular individual is going to remain in the population. That's the idea. It is possible to extend this concept and apply elitism to the best M chromosomes. So the best M chromosomes, 2, 3 chromosomes, are going to remain in the population. And then what happens is that you keep these M individuals in the population, and you use N minus M individuals for in the next from the offsprings, basically. Okay, so the M are going to remain, and the rest of the population will be the result of reproduction. Okay, and this is a high-level description of the genetic algorithm model, and you can see how it works. You start with t equals 0. T is a counter which represents the number of generations. It's an evolution process, and it happens in time, but we are using generations as indication of time. So we start with an initial population, and we evaluate the fitness of the members of the population. This evaluation helps us to identify through selection the best individuals to form a subpopulation or intermediate population, which will be used for reproduction. Reproduction takes place by combining two operations. One is called crossover. It alters, it combines genes from the chromosomes of the parents, and then it applies mutation, which is a kind of noise, in a sense, to alter the genes of the parents. This is going to lead to a new kind of population, which we evaluate again, and we select members for that survive for the next generation. Okay. There are different variants of this idea. So you can use, for example, some algorithms. You produce the offspring, and the offspring survive, and all the parents die. In other cases, you make a kind of comparison between the fitness of the parents and the offspring. So you individuals from your intermediate population P and P star, which is the new population, are compared, and the ones that survive move to the next generation. Okay. It's important to remember that the number of members of the population needs to remain the same. Okay, you cannot extend the population. That's the reason we need to apply this kind of operations. A few words about the convergence of genetic algorithms. It's not so easy to prove convergence. There is a theorem, it's called the schema theorem, which proves convergence. Basically, that means that the best bit patterns survive from one generation to the next by applying the sequence of the different operators, okay? And that would lead to convergence. Everything depends on the probability by which individuals are selected from generation to generation, the probability that the crossover and the mutation are applied. The theorem was introduced in 1975 by Holland, and it's based on the concept of schemata. Schemata are bit patterns which function as representatives of a set of binary strings. So a bit pattern may contain three symbols, 0, 1, or star. So you can have, for example, the schema star, star, 0, 0, star, star, and that represents a number of possible strings of length 6 with zeros in the central position and zeros or ones in the positions where you can see the stars. So you can have, for example, strings like 1, 0, 0, 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, 0, 0, 1, 0, etc. You can produce different kind of combinations, but you have to keep for the zeros in the center remain. These are the standard, and the stars are going to change. The asterisks will change. They can take either the value of 0 or 1. So this schema represents a number of possible strings in this particular population. So I have another example here. You can see the schema. The bits which are 1 or 0 are fixed. They have to remain. The asterisk can change. They can take the value of 0 and 1. So this schema describes, as you can see, these four strings. I hope it's clear. And Holland introduced the schema theorem, which basically proves that in the long run, the best patterns will diffuse to the whole population. I'm not going to present the theorem in detail. It considers a function that has to be minimized, and then we generate strings. And as I said, the concept, it uses this concept of schema to define a bit pattern, and it shows that by applying the different operators, crossover and mutation, although these work probabilistically, it proves that the best bit patterns will survive and will influence the way chromosomes are created, generated by reproduction, and the best bit pattern will diffuse to the whole population. So the whole population is going to improve gradually. Okay. So Holland managed to prove that, and I have the theorem here. It takes each one of the operators, selection, for example, and it shows you how the selection operation is going to change this, calculate the probabilities that the schema will survive through selection. And it also does the same for the recombination. So we combine two parents using crossover. It calculates the probabilities that the best bit patterns will survive, will not be destroyed by applying crossover. And he does the same thing with mutation. Again, calculates probabilities and shows that by applying mutation to specific genes of the chromosome, we don't destroy the best chromosomes in the population. Okay, so by applying this sequence of operations, his theoretical results shows that by going through from one generation to the next, the best patterns will not be destroyed. They will actually penetrate, survive, and influence the way chromosomes are generated from at each generation, and will solve the problem. It clearly explains that the role of mutation. So if you use mutation rate, which is too high, probability goes to 1, then the schemata will destroy it. Okay, so in line with the schema theorem, we guarantee convergence by using small values for the mutation rate. Okay, as I said at the beginning. Okay. It's interesting to make a comparison with other methods like gradient methods. And I talk about gradient methods a lot in neural networks since most of the optimization algorithms, since most of the optimizers which are used in the different packages are basically stochastic gradient descent or standard gradient descent. So in gradient descent, basically the search is based on the concept of gradient. And if we use the negative of the gradient, then the search direction that the algorithm moves is always towards the negative of the gradient. And we use, and to find out how far away, how we should move along the direction of the negative gradient, we use the concept of step size or learning rate, as it's called in neural networks and deep learning. Okay, so if you compare gradient methods with GAs, you can easily see that, okay, basically GA is not affected by the gradient. It's a gradient-free, a derivative-free method. It does not need the direction of the gradient. Gradient descent, we've said a lot that they have problems with local minima, slow convergence, etc., because the gradient sometimes gets very small values. So the weights do not change a lot. You don't have this kind of problem with GAs since they operate in a completely different way. And there have been several attempts since the 90s to use genetic algorithms for train neural networks. So the problem basically is that we are moving from a method that starts from an initial solution, like the gradient descent, and alters the weights of the neural network. You are going into some kind of population method, where you initialize your population, and each member of your population is a potential solution of your problem. So each member of your population represents the parameters of your network, okay? The architecture, the weights, everything. And you evolve these chromosomes, basically you evolve neural network architectures. Or you can only evolve their weights if you like. Okay, it's a very powerful technique, but obviously much more expensive computationally compared to applying stochastic gradient descent. And this is actually the problem that we still have, despite the progress with cloud computing, etc. It's still very difficult to use GAs, difficult computationally, GAs, to evolve architectures of neural networks. It's also interesting to make a comparison with stochastic methods like random search methods. You understand that the genetic algorithm has randomness involved, since we are using mutation, we are using crossover, we apply the operators based on some kind of mutation rate or crossover rate, which is basically a probability. Is done with some kind of probability. Okay, so there is randomness involved. However, the operation of GA is different from a pure random search method. Okay, random search methods are useful because you don't use derivatives again, so they are derivative-free methods. and they based on the use of some kind of noise. But you start from again from an initial solution, and then you evolve this initial solution, okay, by introducing some kind of random noise in a sense. It's not a population-based method. Someone could say, okay, one could introduce a population-based random search. Yes, it's possible. But, and people have tried to do that. Usually it's more effective to use evolutionary algorithms or genetic algorithms instead of a population-based random search. Okay. I have this slide explains the differences between the method. Another idea one could use is to use noise diffusion. It's a group of methods in optimization which are based on the use of noise. And you can actually combine them with gradient descent. So you can have schemes like this one, where the new solution is the old one plus some correction. The correction is based on step size, gradient information, plus some kind of noise. The noise depends again on the type of noise source we are going to use. Is it going to be Gaussian noise? It's going to be uniform noise. What kind of probability distribution we are going to use? And you have the parameter here which controls the noise magnitude, C. And there are different models to control the noise magnitude. And I have an example here which uses an exponential function to control the magnitude of the noise. These are techniques which have been used a lot in optimization and also in a neural network training. And I will give some examples next week in my next lecture about hybrid schemes and advanced learning schemes. Another approach is the so-called simulated annealing. A very good method in optimization, hasn't found applications when it comes to neural network. And the reason is that, unfortunately, it's not in the standard, in the form, the standard simulator is not very effective to train neural networks. It uses, again, the model, the new solution is the old plus some kind of correction. The correction is purely random noise from a uniform distribution. And the new point that is generated is accepted or rejected depending on this kind of probabilities you can see here. So it is probability is 1 if the function values, the new function value is bigger than the old function value. This is because assume this is a maximization problem. Or otherwise we accept it with some kind of probability, where again the probability follows this exponential model. Unfortunately, as I said, simulated annealing does not work in this format very well in neural networks. Different people have tried to produce models. Unfortunately, it's not very effective in high-dimensional spaces like neural networks, where you have saddle points and strong areas with local. Okay, even a saddle point in a neural network can cover a very large area. So it's a kind of flat region where no matter how hard you try to use this kind of idea, it doesn't help you escape from the local. The whole effectiveness of simulating is based on this parameter. It's called temperature, and it controls the noise, the form of the noise, and the magnitude of the noise that you're going to apply at each time step. Usually we use models like the ones you can see here. Compared to stochastic methods, the genetic algorithms can be easily parallelized. And that was actually part of the project that Holland did. And he was trying to find ways, algorithms to manipulate strings that will operate effectively in parallel. Okay, so GAs are inherently parallel and can be easily parallelized. You have to have the right hardware, obviously, to do the work. Okay. Another type of method that belongs to this group is the so-called evolution strategies. Evolution strategy is slightly different from genetic algorithms because in an evolution strategy, we change the chromosomes, but we also change the strategy parameters of the operators, basically, of the algorithm. Okay. we saw that in genetic algorithms, the genetic characteristics of the chromosomes depend on the different operators we have used: crossover, mutation, selection. Okay. In evolution strategies, we still have this kind of operations, but the emphasis is more on the mutation. Crossover is rarely applied. There are variants of evolution strategy which do not use mutation crossover at all. What they all share is a strong emphasis on mutation. This is the operation that is used frequently to adapt the search direction of the different members of the population. Okay. Another difference is that in evolution strategies, offspring can be produced by more than one set of parents. Usually in GAs, we have a pair of parents. These are selected and they reproduce. In evolution strategy, you don't have that. There are variants where you can have many parents, not only two. There are basically two strategies for selection in evolution strategies. It's the plus strategy and the comma strategy, and you can see how they are denoted: mu plus lambda and mu comma lambda. Okay, this is a standard way we represent the plus strategy and the comma strategy, respectively. In the plus case, in the plus strategy, parents are taken into account during selection. In the comma strategy, only offspring are taken into account into selection. All the parents die. Okay. Mu denotes the population size. Lambda denotes the number of offsprings produced per generation. Okay. So it depends what kind of strategy you're going to follow. This is one of the design decisions. It depends on the problem. You may, maybe the parents have some kind of characteristics that you want to maintain in the population. And in this case, a plus strategy may be suitable. Other times, comma strategy is like focusing, to the new members of to the new members of the population. When it comes to crossover again is different. In EGAs, it was just, decide how many crossover sites you're going to have, and then you crossover. One site, two sites, three sites, uniform crossover. Use the crossover mask. Here, situation is slightly different. We have two steps. Step one of the crossover, you can use local crossover, where the offspring is generated from two parents using randomly selected components of the parents. Or you can use a global crossover, where the entire population of individuals takes part in producing one offspring. And the components are randomly selected from randomly selected individuals to create the offspring. Okay. And as I said, you can use evolution strategies without crossover. This is how evolution strategies were introduced, and most of the variants do not use crossover at all. Not local, they work without local crossover or without global crossover. Okay. The second step of the evolution strategy, apply mutation. And mutation is applied into two stages. Stage one, you mutate the standard deviation for the current generation and each individual. Okay, so you have a mutation step size in a sense, sigma, and the step size, the mutation step size at generation +1, the next generation, it depends on the step size on the mutation at generation G, multiplied with this kind of exponential function, and this alters the values of the mutation. You can see the parameters here. This parameter is again follows the normal distribution with mean 0 and deviation 1. Okay, this is another formula that one could use to adapt the strength of the mutation. Okay, as you can see here. And as I said, it's a standard normal distribution. Okay. Stage 2 of the mutation, you mutate the genetic material of each individual. Okay, so now you alter, you work at the level of the chromosome, and you alter the genes in the chromosome by using this kind of equation. All right. In the standard GA here, we had some simple noise. As you can see here, the alteration is based on the values of the mutation you calculated at stage 1. All right. Mutated individuals are accepted only if the fitness of the mutated individual is better than the original individual. So you apply a very strong, hard constraint here. You try mutation. If the mutated individual's fitness is not good, then you don't use it. You throw it away. Okay. And then, as I said, we have selection, and I explained that there are different ways, the plus strategy and the comma strategy. So I have here a few details about each one of these approaches. The plus strategy, you select lambda offspring from new parents, and in the next generation consists of the new best individuals from the parents of the previous generation and the offspring. Okay, so if you want some individuals to survive, you will have to use elitism in this case. Okay, to make sure that these parents will survive to the next generation. And then the comma strategy, the next generation consists of new individuals, but these are all selected from the lambda offspring. Okay. Always the size of the population remains the same. So you have new is the size of the population then at each generation. Okay. And it depends whether this new that will be used in the next generation will contain any of the parents of the previous generation or not. Okay, that's the question. And if you use the plus strategy, yes, it's possible to have some of the parents of the previous generation to the next. If you use the comma strategy, then you only select the members of the population from the offspring. The comma strategy is considered more realistic, has been used in several applications, and this is because no individuals survive forever, so theoretically gives an advantage compared to the plus strategy. But as I said, depends on the problem, because you might have situations where you want some individuals to survive from generation to generation. So you have to think carefully what kind of strategy is best for this particular problem. There are different mechanisms someone could apply. So there are, forgetting mechanisms that can be applied to adapt, basically by adapting the step sizes if you want. So it depends on the scenario, actually. So I have a model here. It shares similarities, as I said, with the genetic algorithm, in the sense that, okay, you have again a population and you have to initialize it and you evaluate the fitness. Some methods are going to use crossover like genetic algorithms. But as I said, most of the methods do not use crossover at all. Okay, they basically use mutation. So the mutation is going to have much more value as an operator than crossover in this case, okay, which is one of the important differences. And the other thing is how you implement, obviously, these kind of operators. As I said, crossover, if you have it, you can have local crossover or global crossover. If you use mutation, definitely you have adaptation. So you adapt, not only you adapt the parameters that control the mutation, but also you adapt, obviously, the chromosomes by applying this adaptive mutation. Some examples now to show you how some of these operators work. I have a simple GA with a small population size 4. single point crossover, bitwise mutation, and that's the form of the fitness. So the fitness in this case is the number of ones in the bit string X. X is a chromosome, has length 8, so there are 8 bits, and you can see on the table the chromosomes. There are only 4 chromosomes. These are the strings, and you can find the fitness. It's easy because the fitness is the number of ones in the bit string. So in the first one, there are only 2 ones. The fitness is 2. In the second one, there are 6 bits. The fitness is 6, and so on. And this slide gives you a kind of scenario that shows how the different operators are applied. And you can see how the operators are applied. So 2 pairs of chromosomes are selected as parents. Let's say that these are chromosomes B and D. And these are the first pair of parents. And B and C is the second pair of parents. This is possible because there is some kind of randomness, so B can be selected twice. There is no problem with that. Parents B and D crossover after the first bit position, and they produce offspring E and F. Parents B and C do not crossover. Their offspring are exact copies of B and C. Okay, so you see F, E, and F here based on the crossover. And then you have, as I said, B and C, which are copies of their parents. Then the next thing is offspring E is mutated at the 6th bit position. It forms the EM, which is the mutated E, and you can see here how it looks like. This looks like, and offspring F and C are not mutated at all. Offspring B is mutated at the 1st bit position, and it forms BM, you see on the slide. Okay, so that's a, the operators are obviously applied randomly, and I have just a scenario here to show you a possibility how this thing will evolve. So what is the population after one generation, and what is the fitness of the members of the population? And you can see what happens here. We have EM, F, C, BM. You can see the chromosome string and the fitness. The fitness is based on the calculation of the ones in the bit string. So it's very easy to produce. And these are the members of the population at the end of this generation. Okay. That's another example of GA to maximize a function. We want to find the maximum value of the function 15 times x minus x to the power of 2, where the parameter x takes values between 0 and 15. To make things simple, we assume that x can only take integer values. We have chromosomes that have only 4 genes, and this table shows you for each one of the integers, 1 to 15, the binary code that represents the integer value. So let's make the assumption that we have the populations of 6 chromosome, crossover probability 0.7, mutation probability 0.001. The fitness in our example is defined by this function, as I said before. And you can see here the fitness function and some of the look for some of these chromosomes. Okay, X1, X2, X3, X4, and 5. This is again a kind of scenario. It shows you the chromosome string, the integer that this chromosome string represents. Okay, the fitness value of this chromosome string, and then the last column shows you the fitness ratio. The fitness ratio is the ratio of the individual's fitness to the population's total fitness. Okay, this kind of ratio determines the chromosome chance of selection. So, for example, as you can see here, X5 and X6, these 2 chromosomes have a fitness ratio of 25.7%, 24.8%. So they have larger probability of selection compared to X3 and X4, for example. Okay. The average fitness normally improves from generation to generation, and we can use the average fitness as a kind of criterion that indicates that the GA progresses well from generation to generation. Okay, so what will happen from generation to generation is that using crossover mutation, the values of the members that will be selected at each generation, we said that the members of the generation are 6. Okay, that's why we have only 6. So at each generation, new individuals will be selected as members of the population that will cross over, and we apply mutation. At the end, what's going to happen is we are going to reach, since this is a maximization problem, we are hoping that the members of the population which will reach the maximum. So the 6 chromosome will converge to this kind of interval, which approximates the maximum of this function. Okay, this is what happens from generation to generation. And roulette wheel, which I said was the most popular ways to apply selection, this kind of function will use this fitness ratio that we have calculated. Okay, so the fitness ratio affects the chances of an individual to be selected for reproduction. And you can see here what happens. We said X5 and X6 have a higher ratio, which basically means that they cover more space on the roulette wheel. And theoretically, this will give them a higher chance to be selected for reproduction. Okay, they will produce offspring, will survive to the next generation. So in our example, we have an initial population of 6 chromosomes. We need to establish the same population in the next generation, okay? Because we basically, no matter what kind of variant we use, we maintain the size of the population the same, okay? We don't reduce it or enlarge it. And to achieve that, we have to span the wheel 6 times, select parents for reproduction. Okay. Once a pair of parents is selected, we apply crossover. Okay. And the crossover is randomly applied according to the point that we are going to select it, and then the parents exchange chromosomes after that point, and they produce 2 new offspring. Okay. If the pair of chromosomes does not crossover, because it's possible, we said that crossover, there's a crossover rate, so we apply crossover with some kind of probability. So if the crossover does not work, then the chromosome cloning takes place, which means that the offspring are created as exact copies of the parents, similar to the scenario that I presented in my previous example. So I have some graphs here to illustrate the process. You have 2 chromosomes, X6 and X2, and you apply crossover after the second beat, and you exchange to produce offspring, X1 and X5. You apply crossover after the first beat, and you exchange. And you can see here some examples of offspring that you can produce. Mutation represents a change in the gene. As I said, mutation is a background operator. It is used to in the standard GA to introduce diversity and make sure that there is no premature convergence, like trapping in a local minimum of the fitness function, basically. Okay. If you use binary, it's random flipping. If you use real values, then you have a probabilistic stochastic model using probability distribution. And as I said, we use smaller values, usually for the mutation. In case of evolutionary algorithms, then mutation is the strongest operator Many variants do not use crossover at all. They always use mutation. So that's an example of mutation. It's a binary representation. We just flip the bit and we can see this happening in chromosome X1. For X2, again, we try to flip the bit and we produce the mutated X2, okay? And this diagram shows you the whole cycle of one cycle of the GA, basically. So we start with generation I, and you have 6 members of the population, and these are the fitness values, and you use roulette wheel, and from the roulette wheel, you can select parents for reproduction, and you apply the reproduction operator to 2 of these, to the parents, and you produce the offspring. On the offspring, you apply mutation, and you produce the members of the population, the next generation, okay? And that closes the cycle. It's an iterative process. Obviously, you run several generations in order to make it work, okay? And this icon is a link to a video, and you can find on the slide explains graphically the nice video to explain the whole process. So that was the end for today. And the material that I used, it's covered in the book, section 7.1 up to 7.6 from the written core text, Navitsky's artificial intelligence, and I have some other sources which are used today, like this book, which is online on evolutionary computation with specific chapters. About selection schemes, as I said, these are very important. There's a nice report from the 90s, which makes a comparison of selection schemes. This is an article about the application of GAs for the steelwork plan, that I used as an example in the lecture, and a very good article about evolution strategies by the person who actually introduced the first one, Schweffel, introduced the first evolution strategy in the 90s. Okay, so it's an article that's available online and gives a very nice overview of evolution strategies. For next week, I'm going to start a set of lectures on advanced learning and evolution, starting with synergistic approaches. What I mean is that combination of techniques like neural expert systems, neural fuzzy systems, and neuroevolution. Okay, so I will start next week with this kind of methods. And if you want to have a look, you can go through the chapters 8.1 up to 8.4 from the core textbook. Okay. So thanks, and I'll see you in the live session. Bye.